which is the fourth teacher that you are meeting during this soft skill course. Professor Alberto Bellini will talk about climate and energy, which is a relevant topic within the context of science of climate change and climate actions. Because, of course, we know that part of the emissions, of the human emissions of CO2 is due to the production of energy, which in turn it's essential for our development. And of course, in the context of sustainable development, reaching a good management of the climate energy nexus, and not only climate energy, but also the resources, part of them are natural resources that are contributing to this nexus. Understanding these implications, this interaction, it's essential. And another essential interaction, of course, it's with economics. Now, Professor Bellini will teach today and will also teach next Monday. As usual, I will attend the lecture. Today, I just wanted to let you know that I am leaving the meeting for some time in between. But please feel free to use the chat and step in with the microphone if you have any question for Professor Bellini. Just wanted to confirm that the slides that Professor Bellini will use today are already available on Virtuale and linked in the course page of my website. And also, of course, I am confirming that the lecture will be recorded and the video be made available on my YouTube channel, I would say early tomorrow morning. I am now pleased to give the word to Professor Bellini and to start this lecture. And please, Alberto, and to the students, enjoy your lecture, and please don't hesitate to put any comments you may have on the lecture and the course on the chat. Alberto, the floor is yours. Thank you very much for being with us today.
Thanks, Alberto, for the presentation. Good afternoon to everybody. It's a pleasure for me to be here. And I will try this Monday and next Monday to provide you a thorough analysis of the combination of climate and energy, and an important part of the topic on energy and climate. Just a moment, I will try to reshare my screen. There was probably some problem. And as Professor Montanari has just said, I will use the slide you can retrieve from our portale. So here we are. So we will discuss of a few topics this Monday and next Monday. So these are the main topics we will discuss in the two lectures. So I know that you are coming from different disciplines. So I will try to provide you basic information on energy and specifically energy conversion. And then we will talk about a quite specific topic that is energy balance. So the relationship between conversion, distribution and use of energy, and specifically the taxonomy of energy. So primary energy, definition and so on, electrical energy and other forms of energy that might be trivial for technological or scientific students, but not for others. So of course, as Professor Montanari has just said, feel free to place questions using the chat or the microphone, especially if I'm using jargon or slang, technical slang that you do not understand because you come from a different discipline. And of course, one of the main topics we will discuss is the relationship between climate and energy, and all the corresponding implications. Then, of course, there will be another session that is very important, that is the discussion on renewables. That is one of the most effective solutions for energy and climate. And I will try once again to provide you information on the different technologies and different solutions we have to fight this problem. And last part, I will try to provide you some interaction. So if we have time next Monday, we will do it together, or I will leave it for you, a personal test. So a personal test on your own impact on energy and climate, assessing your ecological footprint. So once again, feel free to interrupt me, especially about language, because I know that we are all using technical languages, slang, and so on. So please interrupt me if I'm not clear on language usage. So of course, I will start with item 1. And so item 1 is, what is energy? And that is a not trivial question. So I will start with some qualitative analysis, and the qualitative analysis is in these bullets. So energy in our society is the major resource for humanity. Some strange thoughts. Energy is more important than food. What does it mean? Well, think about it. The production on 1 kilogram of meat requires 7 liters of oil. And we can make even more provocative examples, but they are true. So energy is more valuable than drinkable water. And what does it mean? Well, it means that we can produce drinkable water even by seawater, provided that we have 3 liters of oil to convert, to refresh to drinkable water 1 square meter of, 1 cubic meter of seawater. And so this is just to tell you that energy is so embedded in our life that is many times hidden, but is basically the backbone of our communities. So another example, aluminum. If you want to produce aluminum, which is a very complex product starting from the earth material, it requires 5 tons of oil. Then another example, very clear to everybody, car manufacturing. For car manufacturing, you need 3 tons of oil. That is about 1/4 of the overall energy that the car uses in all its lifetime. So once again, hidden energy. You usually think of car thinking of gasoline or any fuel you use during the usage of the car, but you don't think that the manufacturing of the car itself require about 1/4 of the fuel it uses in all its lifetime. And last but not least, the relationship between energy and greenhouse gas emissions is very clear. Around 3/4 or more, we will see specific charts in a moment, is directly related to energy and specifically to the burning of fossil fuels. So energy production, distribution, and usage is the largest driver of climate change. but also of pollution. So both use of fossil fuel and biomasses are directly related to air pollution and, as a consequence, to many health problems for humanity. So this is just a picture to provide you some cues on what is energy and how it is important for humanity. But when it comes to the definition, well, it's very hard to find a definition. I'm here reporting a paragraph, a sentence from Vincenzo Balzani, that is one of our masters, and is of course very reputed researcher. And he's basically saying, if you want to abash someone, ask him what is energy. Everybody thinks of knowing it. However, if you are asking a very sharp definition, nobody will give you a clear and unique answer. Meaning that, as we have just said, energy is mandatory for every process. And as we will see in a moment, it appears in very diverse forms. And there are conversion processes between the different forms, as an example, from mechanical to chemical, from chemical to electrical, from electrical to thermal. But we don't have a clear definition. We don't have a scientific identification of this complex process. We know, because of thermodynamics, that energy is degraded, sorry. So in any process, entropy increases, meaning that things are degraded. And we also know that there are wars for energy. This is pretty clear to everybody. So we know everything, but we cannot define it. So the only thing we can say, to the best of our knowledge, is that energy is a quantity of universal nature that appears in material and immaterial forms, and that cannot be reduced to a more elemental form. This is the best definition we have that doesn't help you to understand what is this very complex process, but I just want to provide you, I just want to set the scene and be more precise in the following. So at first, we will see the picture of the different forms of energy. And to state that, we are opening a very technical problem, that is conversion. So conversion stands for transformation in different form of energy. So basically, we know that there are 6 forms of energy. The 6 forms are thermal, which is very clear and intuitive, chemical, that is pretty clear, as batteries, as an example. And then there is electrical energy, that is also very clear to us, to our personal experience. And then there is electromagnetic, which is quite complex. I will show you a slide in a moment to classify what is electromagnetic energy. But you can think of it as light. Light is electromagnetic energy. Then there is kinetic energy, that is mechanical energy, that is once again very clear concept. And then there is nuclear energy, that I assume is quite clear to every of you. So we have these 6 different forms of energy, and this complex table means the conversion. So in rows, you are in blue from, and in columns, you have in green 2. So as an example, if you want to convert from chemical to thermal, you use a process that is called combustion. So combustion means operation on a fuel, and transform this operation to heat. And this is a very typical process. It's the second industrial revolution. So the possibility of creating heat and using it for replacing horsepower. There are several different examples. You have to analyze them according to this syntax. So as an example, electrolysis here is the process that allows to convert electrical to chemical energy. And to go to something you know very well, I hope, let's look on fireflies. Fireflies are natural process, of course. They come from nature, and they convert chemical energy, that is the protein, the food, the things they are eating, to light. This is a firefly. Another natural examples are muscles. So muscles, of course, convert chemical energy, the same protein or food that we are eating, to kinetic energy. I'm moving my hands. That is exactly the representation of this process from chemical to kinetic energy. Many of these processes are not natural. Some are natural, as chlorophyll photosynthesis. Others are artificial. So specifically, all the processes in red are natural processes, and all the processes in black are artificial processes. So without detailing all of them, of course, unless you have specific questions, what does this matrix tell to us? This matrix tells to us that we have almost filled in all the cells. So we have reversible processes from one form to the others. There are some blank parts. So of course, the blank parts are, as an example, in processes that convert one form to itself. So of course, it's not useful to convert thermal to thermal or chemical to chemical or electromagnetic to electromagnetic. These are not important processes, with an exception, that is electronics. So electronics basically is an exception because it converts electrical to electrical. So it changes the levels, it changes the forms, the nature of the signals, but starts from electrical signals and goes to electrical signal. As an example, the power charger for your smartphone is exactly this structure. So it converts AC electrical energy into DC electrical energy, because you have an AC source on the plug and it goes to a DC source for your smartphone. So all the others are not important, but there is another important specification. The column of nuclear is empty. What does it mean? We do not have technology to convert to nuclear. We cannot convert from nuclear. So of course, unfortunately, we can't create nuclear bombs. So we can convert nuclear energy into electromagnetic energy, and all the others possible combination of forms of energy to nuclear, sorry, from nuclear to other forms, but we cannot connect to nuclear. We do not have this possibility. But apart from that, except that, we are capable as humanity to do almost all the possible conversion. So basically, this matrix, if I can let you understand it, is really a picture of the technology of humanity, and also a picture of the natural processes. Here, there are the most important processes. The processes within the sun, the processes in the nature, like electrolysis or chlorophyll photosynthesis, that are the root of the life. So this matrix, if you understand it, is basically a picture of Earth and of its natural and artificial processes. So, as I said, we go to more specific analysis of electromagnetic energy. As I said, electromagnetic energy basically means waves. So there are waves running in the air or in the atmosphere or in a specific means. And this energy, the energy of electromagnetic waves, is directly related to frequency and wavelength. And wavelength means the length of the wave, exactly what you think of it. And there is an important relationship, stating that they are proportional inversion. So the product between wavelength and frequency is constant, meaning that if you have a high frequency, you have short wavelengths. On the other hand, if you have low frequency, you have high wavelengths. And I will provide you some example to let you understand how this is important. So as an example, your smartphone receives signals that are traveling in the air at gigahertz. So giga means 1 billion. So very, very high frequency. So we are here, about here. So this means very high frequency, so small wavelength. The wavelength is some nanometers. So the wave is completed in a very, very short space. On the other hand, when you go at low frequency, so you might know that energy distribution for electrical system is at 50 Hertz, so 50. The wavelength of electrical energy is 6,000 kilometers. So when we have a line, power line, connecting, as an example, two different cities, within the power lines, there is 50 Hertz signal, and the wavelength generated is starting there and goes to the ocean, 6,000 kilometers. So you don't see the end of the wavelength. And this is very important because formally, you could say that electrical and electromagnetic are the same, and it's true, because they are both waves traveling. But the difference is that electrical waves are at very low frequency, so you can say they are not waving, they are constant. Because in order to see the wave, you must go to very, very high distance. And this is the difference between the two, that for those studying physics or technology, they know that this comes to a different solution of Maxwell law. So they are the same, but they are quite different in behavior. And as you can see, they are quite different in processes that convert one to the others. There was a question on nuclear energy. So the question was, can you explain how nuclear energy can convert to kinetic by radioactivity? You should ask Marie Curie, no? So Marie Curie had a Nobel Prize for that, for showing how radioactivity is also mechanical. So it results in movement, in processes that is basically an effect of the different relationship between the chemical properties of materials. So she and his husband, Pierre Curie, showed that in many particular chemical elements, there is a process called radioactivity that also produces movement within the cells, and this comes from nuclear energy. So this comes from the energy of the atoms and their connections between nuclear and protons. So, of course, these are very complex problems, and I don't want to delve into details because it would not be useful, but I'm just saying, read Marie Curie. You will find very, very nice descriptions and analysis of that, and will be really very, very fascinating. So, and we have now a picture of energy. So I guess that everybody now understand what is energy and what is the basic corners of energy, the 6 forms and the different processes we can use to convert one form to the other, some natural, some artificial. And then we move on. So we are usually talking of production. So you often listen to the word energy production. Well, I hope that you can understand that formally this expression is wrong. It's wrong because you cannot produce energy. And this is because of energy conservation law. Because energy conservation law states that the total energy of an isolated system keeps constant. So basically, you cannot create energy. You know that at medieval times, people was dreaming of creating energy. Everybody has his own magic idea. But this is magic, is not the truth. The truth of science is that energy cannot be created. So the fire is not created. It's just converted with a process from chemical, so to some sort of material, to heat. You cannot create energy. You only convert it. So as an example, when we are looking at this electric vehicle, so a car driven by electrical motors, this is a sequence of energy conversion. So you have a battery that is chemical energy, and you convert the chemical energy into electrical. So the first process is the conversion from chemical to electrical. Then you have an electric motor that convert the electrical energy into kinetic energy, so mechanical energy. And then the wheels are spinning and the car is moving. So these are 2 sequential processes that are exactly in the matrix we have just discussed so far. So I guess you are now thinking more clearly to energy, and energy is basically a sequence of conversion processes. So going in more details, a very important classification of energy is it's about its source. So when you talk about primary energy, what does it mean? It's very simple. So it's an energy found in nature that does not be subjected to any human process. So as an example, oil is primary energy. And why is primary energy, you would say? Humanity is treating it, yes, but it is in nature. So we found oil in nature. So this is a primary source of energy. And of course, sunlight, and of course, wind. So many different types of energy sources are primary energy sources, and they are usually classified in two main categories: non-renewable and renewable. What does it mean? What does it mean? Very important. Renewable means that it can be regenerated within a human lifetime. On the other hand, non-renewable means that it cannot be regenerated within a lifetime. So I guess you understand the difference. So when we have non-renewable energy, as an example, oil, and we are burning it in our car, it is lost. We cannot regenerate it. On the other hand, if we have renewable energy, as an example, photovoltaics, it is used, but it regenerates continuously. So the difference is huge. And we usually forget it, while it is very, very important. On one hand, non-renewable, we are destroying something that will not be used anymore. 1 ton of oil requires millions of years to create, to generate it. And you burn it in 1 second in your car. So it is very important to understand it very clearly. And more important of that, to follow me in the next discussions, is that primary energy can be broadly classified into 3 very clear categories. Electrical energy, that is something we all know and is often confused with energy. So most of us thinks electrical energy is energy. This is not the truth. This is only one of the 3 parts, and is about 1/3. So given 100 energy, 1/3 is electrical. The second third is thermal. And thermal means heat, but also mean cool. Because when you are using cooling system in your house in the summer, this is thermal energy. And the third is transportation. So basically it's gasoline and all the other solid fuels you're using for transportation. These are the 3 forms, the 3 categories in primary energy. And to measure them, we use TOE, that stands for tons of oil equivalent. In the previous slide, there was TEP. This was basically a mistake because TEP is the Italian acronym for TOE, but it's the same. So it's tons of equivalent oil. Many of you knows that energy is measured in joule or in kilowatt per hour. And why we're using TOE? And the reason is very important, because these 3 categories weight in different way. So they're not equal. They're apples and pears. And I will show in a moment what this apples and pears means. There is another question on nuclear energy. I understand nuclear energy is very appealing to you. Unfortunately, I'm not a nuclear engineer, so I'm not so capable of providing many insights. But the question is, assuming it would, why should we convert energy to nuclear? Well, because it's very, very small, tiny. I don't know if you have ever heard or read something of Asimov. In the 1920s, he was thinking of science fiction novels, and in many or every of them, there was nuclear energy as a solution to everything. So basically it means having in very small part, small as an atom, a huge amount of energy. This would be the reason. But this would be basically being capable of converting nature. So being capable of creating a sun. This is what it means. So is, of course, very interesting on one side and very impossible on the others. Can you make an example of electrical and thermal energy? Oh, so this was not so intuitive as I thought. So electrical energy is basically, electrical is a very specific form of energy because it doesn't exist. So you don't use it. So when you think of a bulb, of a light bulb for lighting, this is not electrical energy because it is supplied by electrical energy, but the electrical energy is converted to light. So basically, this is light, electromagnetic energy, the phenomenon you see. But electrical energy is what is inside. So electrical energy, the only forms of electrical energy is power lines. So the lines you have within your house or between houses and cities is electrical energy. This is electrical energy. Voltage and current. This is electrical energy, very immaterial. And why it is important? Because you can transport energy at long distances. So if you want to transport any other forms of energy, it's quite impossible. Quite impossible means with very high efficiency. On the other hand, if you have a power generation plant in, I don't know, Alto Adige, in north of Italy, you can distribute this power here at 500 kilometers distance without any major losses. And this is why electrical energy is so important. Thermal energy is heat. So basically, examples of thermal energy are conditioning in your house. So in a winter, heat produced by the conditioning system in your house is thermal energy, but also cooling in summer is a thermal energy. But most simple, thermal energy is any loss, because any loss is basically as friction as any other, is a part of thermal energy. So I understand now better the question. The question is why electrical energy is considered the primary energy. It is not the primary energy. My slide is saying that primary energy, that are other things, are composed of 3 different categories. So in order to have a clear understanding, primary energy, so energy coming from nature sources, can be classified into 3 categories. And the importance of classification is because they are basically weighting the same. So 1/3 is electrical, 1/3 is thermal, and 1/3 is transportation. But these are not primary energy. This is correct. So I understand your question. This is just to say the overall primary energy can be classified in 3, just to give you clear image at a glance. So I owe you an answer on apples and pears. So why they weigh differently? Well, the reason, sorry for the Italian here, I will try to translate. The reason is that when you produce 1 kilowatt per hour, which is an equivalent unit of joule, so the basic unit of energy, you spend something if it is thermal energy, and you spend more if it is electrical energy. So we can say that electrical energy is more precious than thermal energy. So basically, the benchmark to assess apples and pears is the intensity of emissions. So basically, intensity of emissions means how many units of CO2, carbon dioxide, is related to 1 kilowatt per hour. So when it comes to electrical energy, to produce 1 kilowatt per hour, that is basically an appliance. So your appliance require 2 kilowatt per hour to produce a full cycle. 1 kilowatt per hour results in 307.7 grams of carbon dioxide. If you want to produce 1 kilowatt per hour of thermal energy, so 1 kilowatt heat per 1 hour, it requires for the generation, which is wrong word, remember, so for the conversion, it requires 214.6 grams of CO2 equivalent. And this is why they are weighting the difference. And if you look at this chart, you see the evolution of intensity of emission in time, which is very interesting. This is Italian data. This is why we are using Italian language here, because it's directly found in a report of an Italian association, which is ISPRA. And basically you see how the different intensity of emission is changing in time and why they are decreasing. This is very important because renewables are increasing. So of course, the intensity of emissions is strictly related to the share of renewables you have in the energy production system, where production system is, you know, wrong word, but I'm using it because we are used to do it. So as an example, if you look at the same data from Poland, you would see that data are much higher because they are using coal. They are using large share of coal for energy production. So it's very important to look at this chart, and gives you a quite clear analysis of how are important the relationship between energy and climate. So I guess we have a more clear idea of energy, and we are looking here in more detail. As I said before, you can see here the different pictures from different countries. So you can see that we are performing much better than Poland, as I was saying before, but we are performing worse than the average in Europe, because there are many countries, look at Sweden, look at France, that have very small numbers. And why? Because in France, they are using nuclear energy. That, of course, is not providing CO2. And in Sweden, of course, they have large plants from hydro and other renewable sources. So this is just you to provide numbers that are not only numbers, but are very important to identify the relationship between nature, energy, and climate. So I hope that we have now a quite clear picture on what is energy, and more specifically on what is energy conversion. And I'm now moving to energy balance. That is a step forward. So that is the set of processes that allows us not only to convert energy from primary sources to electrical, thermal, or mechanical energy or other forms, but also how to distribute this and how to use it in our life. So another very important section to understand the world of energy. So it's 4:30, so I believe it's time for a break, and we will take 10 minutes break, and then we will start again. We start again with section 2 on energy balance.
Thank you very much, Alberto. Thank you.
So good afternoon. Once again, we will start in a moment. And of course, if you have comments or questions, feel free to use the mic or the chat for questions. So we will now start section 2, dealing with energy balance. And of course, the main purpose of this section is to let you understand what is energy balance. And basically, it's made of different sections of the energy lifetime. So, as was asked before, electrical energy is a very peculiar form of energy. And it is basically an intermediate form. It's not either a source, so it's not primary energy, but it's not even final use of energy. On the other hand, thermal energy, kinetic or mechanical energy are typically final usage. And of course, primary energy is a source of energy. But electrical energy is so important that many of us often confuse energy with electrical energy. I myself, of course, because I'm an electrical engineer, so for me, energy and electrical energy are synonym. But in general, electrical energy is very important because it's an intermediate form that is used to bridge other forms. So it's used to bridge between the others 5, but also for the second bullet, which is very important, that is transmission. So you can transmit energy, transport energy at long distances, even overseas. So we can transport energy crossing the ocean and going to island. So electrical energy is really, really very flexible. But there is an important word also that is regulated. And this is very important because on one hand, if you have mechanical energy, you have some intensity. And it's not that easy to regulate the intensity. And the same stands for heat. It's not so easy to increase or reduce heat. You can do it, but not so easily. On the other hand, electrical energy can be regulated. I have already made an example. I will repeat it. So your power charger is regulated electrical energy from AC 230 volts to DC, 5 DC volts or 10 DC volts. It depends on the final usage you need. And easily means with very high efficiency. What does it mean? So if you look at the power charger, it regulates the energy, the electrical energy, with 94–95% of efficiency. Meaning that if you have a power charger, on one side you have your smartphones. On the other side, you have the plug and you have the electrical energy network. So the point is, if we are using 100 units of energy, so we are paying the bill, meaning that each unit of energy has a cost. So just to give you an idea, 1 kilowatt per hour is about 0.2 euro. So it's very clear. It's bill, it's money, it's environmental impact, because you need the use of nature resources to produce this kilowatt per hour. So the point is, what is efficiency? Efficiency is the ratio between what you have here and what you consume at the beginning. This is efficiency. So efficiency is the ratio between 95 and 100. That is, of course, 95%. Just to give you an example, your thermal engine, that is the engine in a typical gasoline car, has an efficiency less than 30%. So what does it mean? It means that 100 is the energy in the gasoline, and you have 30 converted to kinetic energy, so wheels spinning, and 70 goes to heat. So it's lost. It's just eating the air without any usage. So here, of course, the 5 is lost. In fact, if you take with your hand the power charger, it is slightly eating, because part of the energy is converted into heat. So these are losses. But 95% is a huge number. There are basically no artificial process with higher efficiency. And be aware that nature has a very low efficiency. So just to give you an example, let's compare photovoltaics to chlorophyll and photosynthesis. So they are both using sun, and they are converting the sun to something. So both are starting from the sun and producing something. So in top is chlorophyll, so is the plants, is the nature using sun to provide protein and energy with foods. So this is about 0.2% of efficiency. So only a tiny amount of energy is converted to protein or whatever. Quite tiny, but very important. Life on Earth depends on chlorophyll and photosynthesis. And this is a natural process. So you don't have to think that natural processes are very efficient. They are important, but they are not so efficient. On the other hand, your power charger has an efficiency of 95%, which is wonderful. And let's think of photovoltaics. You all know what is photovoltaics. We will have next Monday specific session on the different technologies for renewables. So we will, of course, detail largely photovoltaics. So it comes with the same input, which is sun. You know what is the power of sun? Is very clear. 1 kilowatt per square meter. So in every square meter in the Earth, the sun radiates 1 kilowatt. That is very clear. So when it comes to chlorophyll and photosynthesis, it comes to 0.2 conversion. When it comes to photovoltaics, it's 20%. Well, we will see it in detail. It's ranging from 10 to 20%, depending on technology. Of course, you have many different technologies and different flavors you can use, but still is amazing if you think about it, that we are performing 100 times better than nature, and still we are using oil from underground. This is not silly. So we have the technology to perform 100 times better than nature, which feeds all the human species and other species from billions of years. And we are performing better, but not better, 100 times better. And this is something I would like you to think about it, because it's really very important. So coming back to efficiency, high efficiency processes. So electrical energy is very flexible and very important for that reason. And then there are other very important, bullet 3. So you have transistors. What does it mean? It means that you have a valve that can convert a huge amount of energy with zero energy. So basically, with a valve, you can control the flow of something. As an example, the flow of water, the flow of air pressure. And of course, to controlling the flow, you need energy. When you move the valve, you need energy to switch it on, off, or partly on. With a transistor, you are controlling the flow of electrons. So the flow of current, the flow of electrical energy. Electrical energy is the flow of electrons. So basically, you can control the flow even at very high power. So as an example, when you have in a railway station, a train, it uses thousands of amps, very huge amount of energy. And you can control the flow with tiny energy. This is the transistor. Another peculiar characteristics that is only for electrical energy. And of course, there are devices that can convert bullet 4 electrical energy into mechanical energy, that are electrical motors, and vice versa, that are electrical generators. And once again, the efficiency is as high, sorry, there is a mistake here, as high as 90% or more. So what does it mean? Well, here there is a very, very specific thing that I will try to let you understand with a very provocative example. So the first thing is that when you have an electric vehicles, you are using 90% of the energy in the batteries, and 10% only goes to heat. When you have a thermal driven car, it's driven by a gasoline engine or whatever, it converts less than 30%. So 70% of the energy in the fuel goes to heat and many other pollutive elements. And this is a clear difference, but it's not the only difference. There is another that is even more important. So an electrical machine is reversible. What does it mean? The same device can be used to convert electrical energy into mechanical energy, or mechanical energy into electrical energy. So basically, the same device that is electrical machine is reversible, meaning that it's named motor when it converts electrical into kinetic, so mechanical energy. So it spins. And it is called generator when it converts kinetic into electrical. So the first example, the blue line, is the electrical motor in an electric vehicle. The second example is a wind generator. So you have wind spinning a turbine that is connected to the machine, and the machine produces electricity. So I'm not sure you understood the importance of that. So the device is the same. What does it mean? Here it comes the provocatory example. if the thermal engine in your car was reversible, when you brake, it produces gasoline. So when you brake, it produces gasoline. Because if it would be reversible, when you brake, you go in this direction, so you produce the fuel. While in an electric vehicles, it works. So when you brake, you recharge the battery. When you brake, you recharge the battery because the device is the same. So the same device can be used for the reversible flow. And I repeat, thermal engines are not reversible. Otherwise, when you brake, you would produce gasoline. That is just a miracle. I don't want you to think about it. This is just a provocatory example to show that this is really outstanding. So the other peculiar feature of electrical energy is that it is the same device that is reversible. So it's really, really very flexible, and many, many things comes from that, and you can just imagine them. Engineers are working on that, and still the floor is very open for any creativity or imagination you can have. So last item is power electronics, and I guess it's very clear. So power converters, power generators, power charger, they are also very, very effective. And of course, the error is propagating, so as high as 90% or more. So this is electrical energy. And this picture shows you another important part. So we have said that electrical energy is very important because you can transport energy at very high distance. So as an example, we say this is Trento, where we have a large power plant, and this is Bologna. And we can use power lines. These, of course, are power lines. You all have seen them, that cross all the regions coming from Trento to Bologna. And the important thing is that you can transport energy at long distances, not only at 95% of efficiency, but even more. So basically, all the amount of energy you have in Trento goes back to Bologna. So a very specific technical point that I just want you to provide to you, to give you insights. There is a very, very interesting storytelling. Have you ever heard of the War of Currents? The War of Currents. There is also a movie. The War of Currents was held in 1885 or so, between Nikola Tesla on one side. So the two fighters were Nikola Tesla and Westinghouse. And on the other side, Edison. Thomas Alva Edison, the discoverer of light bulb. So basically, Edison was very convinced. So setting the scene, in 1885, electrical energy was not used. So if you think about it, you now have electrical energy everywhere. in your bedroom, you have a plug that's 20 centimeter because you want to have electrical energy everywhere. In your smartphone, you have electrical energy in the battery. So we have now electrical energy everywhere. In 1885, there was no electrical energy. So lighting was a problem because you need oil or similar to produce light in houses at night. So the nights were very dark. And even simple things were very, very terrible. So at that time, Edison was the discoverer of the light, but he required electricity for its light bulb. And the point was, he was thinking of providing a network, power lines of energy to every house using DC, so direct current. On the other hand, Nikola Tesla and Westinghouse were thinking of AC. And there is a movie, which of course I advise you to see, because it's really very, very funny. So you see that the comparison was made on, of course, on economics, but also on many different things. So as an example, Edison thought that DC was not killing people. On the other hand, he said that AC was killing people. And there were many, many funny things, like horses burned by electricity or other different things. But the point is that both kill people. And this is the important information I want to share with you. When the level is higher than 50 volts. So in terms of safety, you cannot touch anything which has a level higher than 50 volts. So as an example, the battery in a car is 12 volts. And the reason is that, because this is not dangerous for people. On the other hand, 50 volt is dangerous. So it's not DC or AC, it's the level, it's the power. But the point is, you see here that in power lines, there are 380,000 volts. So it's a huge amount of energy that, of course, is terribly for people. It's killing people, even if you go at some distance from the power line. So please be aware that they are very dangerous. But the point is, and why we are using such a high level, while on the other hand, we need some hundreds of volts. So within a house, we have 220. And in a plant, we have 6,000, which is not small, but it's not 380,000. And the reason is very simple. Electrical power is basically a product between voltage and current, and the losses, the losses are directly proportional to the current squared. So basically, what happens, if you can increase voltage level and decrease current level, keeping the same power, so let's assume we have 1 billion watt here, and we want to transport 1 billion watt there, we could transport them with, I don't know, 1 million volt times 1000 ampere, or the other way around, 1000 volt times 1 million ampere. The two things are very different because there is square current. So of course, there is 1 million times difference for losses. So of course, the best solution for transport, for transmitting energy, is use very high voltage and then low current. And this is the point that determines the end of the war. DC cannot be transformed. AC cannot be easily changed in level by transformers. So there is a device called transformer that can be used to easily convert the level of voltage and then current easily. In DC, there is no transformer. So this is why Nikola Tesla and his induction machine and Westinghouse have had a large success. And the end of the story is probably even more strange to you. Nikola Tesla and Westinghouse also designed and realized a power generator. Of course, they need power to boost the light in all the houses. And they built a power generator in Niagara Falls. So at the end of Niagara Falls, there is a turbine converting the falls, the waterfalls, into electrical energy. And this is a generator created by Tesla in 1990, I don't remember exactly the year, and is still there, So, of course, some maintenance have happened in time, but this is timeless technology, and this is rugged technology. So this is electrical energy, and this is electrical energy distribution. So I hope that now you have a clear idea of what is distribution, and it works even in the ocean. So you can transfer a power line in the ocean, and the advantage there is that you can use one single power line because the other is the water. So it's very easy to transfer power in water. So I guess energy distribution is clear, and then we move to the overall balance of energy. So please remember conservation law. Energy is not created, energy is not destroyed. So we are in an isolated system called Earth, and what is inside is inside. We cannot convert or create new thing. We only have a source, which is the sun, which is used for everything. As an example, for food, by vegetables, by plants, by chlorophyll and photosynthesis. But we cannot create gold like they thought in medieval times, or we cannot create any resources. We can only convert things. So stick to the energy. We have basically three parts in the lifetime of energy. The first part is wrong, is energy production. Is wrong in the sense that it's not production, creating from nothing, is conversion. So it's converting oil from chemical energy in the oil to something. And this is phase one, production. That is, I repeat, wrong word to specify the creation of energy that is not primary. And of course, it starts from primary energy and it converts to something else. Then there is distribution, step two, task two of energy lifetime, that is always the same, is electrical energy. That's why I use the power line, because distributing energy in any other form is impossible. Well, it's not impossible, but think about transferring mechanical energy from Trento to Bologna. So how can you move some kind of energy from that point to that distance? Or, I don't know, thermal energy. How can you propagate heat in a larger space than a house or something more large? And then, of course, there is task 3, which is final energy use. So, as I said, electrical energy cannot be used, so you convert it in others. So, light bulb are producing light, or motors, electrical motors are producing movements, or any other forms of final energy use. So we now have a clear picture, I hope, of the lifetime of energy, and this is called energy balance. So on one side, you have the need of energy, the energy demand from finally energy users, that is the sum of demand of energy for houses, sum of demand of energy for transportation, sum of demand of energy for industry, mainly. These are the main components. This is, on one side of the balance, the list of finally energy usage. And on the other hand, you need to produce exactly this amount of energy. So if the amount of energy of Bologna is 1 terawatt per hour, I'm just giving numbers, you need production plants to provide 1 terawatt per hour. And the important thing that this is instantaneous. So in every second, in every millisecond, you need exactly that energy. If this doesn't occur, you have a blackout. You are very young, so you don't understand the word blackout, but I'm sure Alberto and myself have a very clear image. Blackout means you don't have electricity in your house. And when I was young, this unfortunately happened, not often, but sometimes. What does it mean? It means that there is a difference between production and demand. So demand is higher than production, and it doesn't work. You do not have storage. This is instantaneous. So in every instant, you must produce exactly the amount of energy that is used by final users. You cannot produce less, but you also cannot produce more. And why? Because if you produce more energy than what it is demanded by user, this is lost. And this could be a trivial problem, but it's a huge problem. So I'm giving you an example. You have an electrical car and you are braking, okay? So as I said before, when you brake, you have to convert this energy, because braking is an energy conversion. So how you convert this energy? Well, in a typical braking system, you convert it to friction. So you have special tools that converts the mechanical energy into friction, so heat. So you very quickly convert with the braking system energy to heat. Let's assume that we don't have braking system. We have an electrical vehicle, so when we brake, the energy goes back to the battery. So we don't need brakes. So let's assume that we are braking, but the battery is fully charged. What does it happen? You don't brake. You hit the wall, if you're lucky, or even worse, because you need to have a destination, a repository for the energy. Energy is not something immaterial, it's energy. So it needs to be converted. And if you don't have a repository for that, it is impossible. So even producing more energy than what is needed is a problem, because you need somewhere a repository. So quite often in the network, there are systems where you just burn energy. So when you have excess of energy, you burn it, because otherwise, if you cannot burn it, this would break the power lines. So if you have in the power lines more energy than what is needed at the end, you break the power lines. Just as like as if you don't have a braking system in your car and your battery is fully charged, you just don't brake, because you cannot convert mechanical energy into anything. So you keep on spinning the wheel. Okay, so this is energy balance, a perfect combination of different conversion, starting from production, meaning conversion from some primary sources to a form of energy, distribution, and final use. And you need to have a perfect equivalence between production, wrong word, but you understand me, and final use. So we go to more details. Production, here I'm stating the right word, conversion of electrical energy is always the same process. So you probably won't believe me when I'm saying that power plants from gas, power plants from coal, power plants from nuclear are the same. What does it mean? Well, it means they have the same stages. In the plant, of course, the plants are very different, but there are the same 3 stages. Stage 1, heat production. So you convert some primary energy source, coal, gas methane, or nuclear, into heat. First stage. Second stage, that is exactly the same, you have a thermomechanical conversion. So you convert the heat into movement, into kinetic energy. And this is Industrial Revolution 1. So you have the steam engine, and that is basically the same that was discovered in 1800. So you have heat, and you convert the heat into kinetic energy, movement. And this is why they are the same, because what is changing is the way you produce heat. So what if I would produce heat from the sun? Yes, it is the same. You just change the first part, you produce heat from the sun, and it works. So you just use heat to produce mechanical energy, and then there is stage 3, which is electrical energy, because you remember we need electrical energy for stage 2 here. So in any case, we need the system. It is the rugged system working since 1800 that is electromechanical conversion. So it converts mechanical energy, turbine spinning, to electrical energy. That's why power plant is the same. Power plant is the same. There's a question on the thermomechanical conversion. Doesn't the thermomechanical conversion waste a big portion of energy? Yes, of course. And that's why, very good question. So I'm not stating here that the overall efficiency is 95%. The overall efficiency, so you remember, efficiency is the ratio between the energy you have here and the energy you have here. So it's out energy divided by in energy. So the overall energy, the overall efficiency here is the product of the efficiency of the 3 stages. So we have an efficiency for stage 1, an efficiency for stage 2, an efficiency for stage 3. We know that the efficiency for stage 3 is 95 or something, but we also have efficiency for stage 2, which is quite low. Surely less than 30%, probably less than 10%. So the question for your colleague is stating, cannot we do something else? So as an example, convert directly the heat into electrical? Well, we go back there. Can we convert heat to electrical? So thermal energy to electrical energy? Well, the answer is yes, but can you do easily thermoionic emission system for conversion of thermal to electrical energy? Well, yes and no, in the sense that this is a viable, but it's not something so robust, so rugged than steam engine. So yes and no. It's a problem. Your question is very, very well placed, but we must do with that. But we have alternative solutions. So what about if we use wind generators? What are doing wind generators? They are overcoming the problem. So we are entering in the system directly in stage 3. So we have directly a mechanical system. So we do not need, so the input is mechanical energy. So we do not need to convert heat into mechanical energy, because the prime mover, the first source of energy, the primary source of energy is wind. So it's a primary source of mechanical energy. And then we need just stage 3, and we know that the efficiency of stage 3 is 95%. So yes, we have a good answer to your question, but this is not related to heat, it's overcoming the heat. Then we have another solution, and the other solution is photovoltaics, that even bridges the third stage. It goes directly. You just convert sun to electricity. You do not need any intermediate conversion. It's photovoltaics. It's an effect we will detail next Monday with technological solutions for solar panels. It's really incredible. I repeat, 100 times better than nature, 100 times better than photosynthesis, chlorophyll in photosynthesis. So let's think about trees. They would dream to have this technology. They don't have it, but they still live very nicely. So really think about it. So this is just a picture to say you that we are now, I hope we now have a clear vision of energy balance. And we have had some ideas on this part, and we can say that basically all the power plants that we're using to produce, so to convert energy from some primary source to others, are basically made of 3 stages. So heat, mechanical, and electrical. Very simple. And I repeat, you could use solar energy to produce heat, but once again, to go back to the question, how can we improve the efficiency of the steam engine? While the efficiency of the steam engine is stated by Carnot law, that says that what is important is the difference of entering it with exiting it. So in order to have an highest efficiency process, you need very high temperature. So the only problem of solar-made power plants, not photovoltaics, solar-made to produce heat, is that you would need 1,000, 2,000, 3,000 Celsius to have high efficiency in the steam engine. And as you might understand, it's not that easy to have some fuel, some kind of water at 1,000 of Celsius to have a very high efficiency steam engine. That's why coal, gas, and of course nuclear are much better, because they can easily provide very high temperature that result in a higher efficiency of the steam engine, but still higher efficiency mean 20% or so. Okay, so and this is the example of the solar energy, using solar to produce heat. That is exactly the same, with the limitation that air temperature is not as high as before. So this is a problem. Problem in the sense that it even doesn't work. So if you cannot overcome something around 500 Celsius, it doesn't work. So this is the reason why there are some solar plants in the deserts where you can rise temperature to some 100 Celsius, but as an example, you cannot build a solar plant in Bologna, because it's not that easy to reach this temperature. And these are examples of some heat production. Of course, typically you're using parabolic through or something similar, because this increases, concentrates the energy of the sun in a very specific position where you reach higher temperature. So as an example, here is the kernel. So basically you are increasing the temperature in the kernel, and you can go as high as some 100 Celsius there, and it works, of course, better in the desert than in the north of the earth. And the other are different flavors for the same idea. So there is another question. For electrical cars, how did they manage the problem of having full charge when the brake is used? The brake means brake, so B-R-A-K-E, not brake, B-R-E-A-K, I guess. So they have braking system. So the solution is very trivial. So my provocatory example was that in your car, you don't have braking system, but in real electrical cars, you have braking system. So when the battery is fully charged, the energy is converted into friction. So you brake because of friction. So you convert mechanical energy into heat. But when the battery is not charged, you recharge it. Then when it is fully charged, use the standard brakes that are in thermal engine, and you brake. Is this clear? I hope that there was just a mistake on brake. Okay, so then we, from now on, we'll see some numbers. I hope you like numbers. You know, we engineers like to use numbers because they provide very immediate information and very clear analysis of the history and of the problems we have. So I'm going very, very late in time at the time of Edison and Tesla. So we are going back before electrical energy. So summarizing what we've said before, there is Industrial Revolution 1, which creates the steam engine. That is breakthrough innovation, because you don't need horsepower or manpower, because you have steam engine. Then there is Industrial Revolution 2, and the Industrial Revolution 2 is electrical energy. So when we go back to 1800, we do not have electrical energy. And what is this chart showing us? It's quite complex, but I will try to let you understand it deeply. So we have different colors and percentage. So in y-axis, you have the percentage of energy. And in x-axis, you have time. So in 1800, about 100% of energy was produced by biomasses, so by wood mainly. Of course, people is using wood from long times, of course, before than 1800. But you see, in 1800, there is a very tiny gray lines, which is coal. So they were starting using coal because in steam engine, for the reason we said before, they required higher temperature. So coal is producing higher temperature, and more than this, higher energy density. So for a small amount and weight of coal, you have larger energy than wood. So in 1800, this was the situation. And what happened from there to nowadays? Well, I hope this image is very clear. This image is showing you the shares of energy in time. So you see that when the oil ages started, so we are here in 1900. So oil was discovered. Well, oil existed from always, but it was discovered the way of using it industrially. So you see that Industrial Revolution 1 is based on coal. So the gray lines was increasing until the oil age, and it was as high as about 60%. So before oil, 60% of energy was produced by coal and 40% by wood, by traditional biomass. Then we enter in the oil age, and what is happening, you can clearly see there from the blue line. So oil increases its use since nowadays, where it covers about one third of overall energy demand is covered by oil. About 20 or something is covered by coal. Then there is small use of traditional biomass. Then there are other forms. What are the other forms? Gas, pink, that is methane. Then we have other very small form. The red one is nuclear. So this one is nuclear. Then there are tiny things, solar, wind, renewables, tiny things. You really don't see them. And this is something you probably do not perceive. We have an idea that renewables are increasing, are covering our demand. It's not true. It's not true. We still have a large energy balance covered by coal, oil, and gas. They're covering about 80, 85 or so of energy. There is also light gray, blue gray, I don't know how do you call this color, that is hydropower, which is very traditional renewable sources. This is Niagara Falls, hydropower. You have waterfalls and use with turbines the power of hydro. This is renewable, yes, because water is regenerated in itself. So this is renewable. So of course it creates problem. Everything creates problem. When Niagara Falls plants was created, people were saying that Niagara Falls were not as fine as before. Yes, of course, because the waterfall is decreased, because of part of the energy is converted into electrical energy, and you don't have the same waterfall as before. So everything is an impact. There is no technology, no artificial things that has no impact. This must be very clear. But anyway, you can include hydro in renewables because this is a renewable energy source, but still the sum of them is very, very tiny. So I would imagine you have now some curiosity. So you could say, well, this is not a fair way to show data, because of course I assume that in 1800 the absolute value is much lower than in 2019, and it's true. The overall demand of energy in 1800 is lower than the amount of energy in 2019. And try to guess it. What is the ratio? So let's assume that the energy in 2900 was 100 units. So what you think here, 100 times, 1000 times, 10 times, what you think is the order of magnitude between 2019 and 1800 in terms of absolute values? Do you have some guess? Please use the chat. No guess? 100. 100 times. 10,000. 5,000. Oh, I'm just asking a ratio. So not an absolute value, but the ratio between 1800 to 2019. So you are all starting from 100 to more than 100. Well, this is not the truth. The ratio is much lower. And this is another thing that shows us our wrong perception. We are not using, well, we are using more, but not that more. We are using 30 times more. And here is the same picture in absolute value. So the same picture as before in absolute value. So you can see that the absolute value in 1800 is about 5,000 terawatt per hour. So terawatt means 1,000 of billion. So million of million. So, and of course, these 5,000 were all in wood, were all in traditional biomass. In 2019, things are different, and we have about 30 times more, and we have, of course, about the same biomass. This is important. Oh, you see, about the same, of course. Wood and others are just doubled, but nothing more than doubled. And then you have many, many other sources, among which, of course, the strongest is oil, that weighs as 53,000. But this is not 10,000 more. It's 10 times more than 1800. So oil alone is 10 times more. So we have a bad perception. I'm not criticizing you. Everybody would answer like you have done. I'm just showing you that we all have a bad perception. Numbers are not increasing so much. What has increased so much is the use of oil. So it's the use of something we are burning and it's lost forever. So that's the point. So I hope you have now a clear vision on energy history, on the sorry, I've recently read that in 2090, renewables overtake fossil fuels in Europe. Yes, but for electricity. So don't forget that we are talking of energy. So energy, there was a question at the beginning, is 1/3 electrical, 1/3 thermal, and 1/3 solid for transportation. So you are talking of 1/3. In the 1/3 of electricity, it's true. We have quite good news coming, especially in Europe, but Europe is not a word, and we are looking at the word. So once again, it's important, but this is just a small piece of the overall picture. And yes, it's true. In Europe, we are performing well, and for electrical energy, for the first time in 2020, there was an overtaking. So fossil fuel were less, slightly less. So they're basically the same than renewables. Good news, but don't overtake it. It's just a piece of the part we must perform much better. So let's go on with numbers. I hope that you can understand how they are helpful. Well, actually, it's 5:45, so it's time for the second break. And I will break before starting discussion on the numbers you see in recent times. So from 1990 to nowadays. So we will have a break for about 10 minutes or so. So probably we will restart the lessons at 17:55. And as I said, we will analyze some charts with relevant data of energy. And we start from this picture showing you the primary energy supply by source. So meaning but which natural source is used to produce this primary energy in a short time, so the last 30 years about. So this time frame is very important because you probably know that in 1919 there was the Kyoto Protocol. So we can say that starting in 1990, the problem of climate, the problem of environmental impact was broadcast, was very clear in all the world. But still, this chart is showing us a very terrible conclusion. So the amount of energy supply has increased. So basically, we had about 8,000 million tons of equivalent oil in 1990, and we have now about 14,000 million of ton of equivalent oil per year. And so the increase was very important. And how you can see here, the increase was mainly made of primary and secondary oil, the yellow part, and by coal that has increased, and natural gas that also was increased. And you clearly see here that the only exception to that was the economical crisis in 2008, where, of course, the amount of energy decreased, but this decrease was made because of economical problems not of virtuous actions. And so not very good news. And of course, if you would look at the chart here, you would see a break because of COVID pandemic. And the break is quite important. There was a decrease of energy consumption of about 8%. This is preliminary data, because of course we don't have official data for 2020 so far. But the bad news is that we had just 2 weeks ago a news saying that greenhouse gas emissions that were decreased because of this hole have already reached the level before the COVID. So we have already overcome the level of emissions of December 2019. So the hole created by COVID is not resulting in a reduction of emissions. So still very bad news. So I want to provide you clear picture of energy balance. So you remember we have 3 different parts. So now I'm showing you a pie that opens the first stage. So the part of energy conversion or energy production, if you prefer. So we can say that in the world, we have about 2 tons of equivalent oil per inhabitant. 2 tons of equivalent oil per inhabitant. And this amount of energy, remember, primary energy, not only electrical, like it was asked before, is made of about 90%, sorry, it depends on how we consider biomasses, if biomasses is renewable or not renewable. Because if biomasses is considered as renewable, we have 80% of non-renewables and 20% of renewable. If we don't consider biomass as a renewable source of energy, of course, the share is different. And the point is, and why biomass is either renewable or not renewable? Well, there is some controversial in that, because, of course, biomass has a zero emission balance, because they basically are fixing emissions in the wood or others, and then releasing when you burn it. So the balance is zero. You don't have additional emissions. You just have a complete balance, zero, with the use of biomass. But the point is time difference. So you can have biomass that are produced in 30 years, 40 years, and you burn it in 1 second. So it's renewable, but it's not really instantaneously renewable, like solar or water or wind. So many things that the only renewable energy sources are solar, wind, and water. Where water means tidal energy, and so energy from waves in the water, and hydropower. But others think that biomass can be considered renewable. So this is just to clarify my statement before. So anyway, it's a very bad situation, because 80% or 90% is still terrible. Okay, these are numbers in 2017. So like we were saying before, things are slightly improving, but really slightly. And of course, this is pi 1. So it's the pi in balance of production. You may have noticed that the overall number, which is about 14,000 million of ton of equivalent oil, is different from the use. And you might think, well, you explained as before, they must be the same. And they must be the same instantaneously, while these are cumulative numbers in the year. time frame. So what is the difference? Well, these are losses. So the difference between the two numbers are losses that are losses in transmission, but also losses in many other devices in the network. So as an example, when you convert energy from electrical to thermal and whatever, there are losses that are important. So don't mind about this difference. This is mandatory. It's a physiological part of the system. So the question is, why don't you consider geothermal energy in this pie? Because it's 0.0.0.01. So it's a tiny amount of energy in the overall. So that's the reason for that. There are many others, but you see renewables are 2%, all the renewables, and geothermal is here. So it's a tiny part of that. So renewables means wind and photovoltaics together. So these are the problem. So we go forward and we look at the same numbers on a time frame perspective. So basically the pie was made here in 2017, and we are now looking at the pie in time. So how have things changed from 1990 to 2017? They don't change. That's the bad point. So the pie would be almost the same in every year you catch it, because what you can obtain from this picture is that, well, there are slight changes. Coal is increasing then decreasing, natural gas is covering the coal, and oil is slightly changing, but basically the only conclusion is that this tiny line that is renewables keeps tiny. So that's the point. And of course, nuclear, we all know, has had some problems after Fukushima and whatever, but things are constant. So this is the conclusion of this chart. And against perception, we are all thinking that things are changing quickly. This is not the truth. Numbers are the truth. So when it comes to the final energy use, as I said before, it's quite easy to have quite clear classification. So primary energy can be classified into electrical 1/3, thermal 1/3, and transportation 1/3. And the same picture is roughly seen in the final energy use at world level. Remember, we are at world level, so a mixture of very different things. US people, Kenya people, Congo people, all together. So what is the pie saying to us? Well, still about 1/3, 1/3, 1/3. Not really, but 30% is used in industry, 30% in transportation, mobility, and more than 30% in service. So the last 40% is mainly energy for houses, which is residential. Don't forget, energy here is primary energy. So it's both heating and cooling and electrical energy. So it's not only lighting or TV set, but it's also heating and cooling. That requires, of course, huge amount of energy for each houses. And other are, of course, energy not for residential, but for services. So for instance, to produce the energy for the university building or for the buildings for public administration and so on. So these are the numbers. So to provide you an idea, the energy is used in these three main destinations: transport, about 1/3, industry, about 1/3, and buildings, about 1/3, more than 1/3. So, and once again, things are constant. So if you look at the time, we believe, okay, we are very good at designing new buildings, so we are expecting that buildings are reducing their impact. And it's not true, because there is a reduction on the residential part, but this reduction is very small. And the same is, you see here, specific definition on commercial and public services. That was the other parts before. And again, transport is even increasing. And industry has changes, of course, because of different economic crises. So you have differences, but what you have as at a glance, you see that it's constant. So nothing is changing. And so there is a storytelling that is saying, okay, we are very good, we are improving, we are better, but it's not the truth. And that's really the most important point I want to share with you. So once again, coming back to primary energy demand by source, we see that number are here and are increasing. So once again, at world level, we started from 10,000, and here we are now about 13,000. But the most important information here is forecast. So you see there is historical part. So these are, sorry, these are real numbers, and these are estimation. And this is the so-called business as usual. So if we are going on keeping the same pace as in the last 30 years, so if we are performing like we are, we will increase consumptions and energy demand. And why? Because population is increasing, and more important, because there are countries less developed that requires more energy. So as an example, in China, energy demand has almost doubled in the last 10 years. And because both of population increase, plus most of that because of wealth increase. So they are wealthier and they require more energy, because they see that there is a gap between the energy consumption per person in Europe, in USA, and in China. So they, of course, increase the consumption. And this is a pretty natural behavior. So very, very bad news. So just a few words on Italy. I believe we are interested in looking at ourselves. And so we can make some comparison between the world and Italy. So first difference is the average. So you remember that in the world, the average was 2 tons of equivalent oil per inhabitant. In Italy is 2.5. So of course, in the overall weight, the overall mean, there are countries like Congo or Kenya or whatever, or Angola with very low consumption, and countries like USA, where this number is 7, about a ton of equivalent oil per inhabitant. So Italy is here. And you can see that Italy is performing slightly better than the average. So the average of renewables is 6%, not 2% as before. But still, renewables and hydro are 8%. Of course, we do not have nuclear. So here, nuclear is 0. And we have the same average for biomass. And you see that we have a large share of natural gas, as you probably know, and very slight part of coal, which is very good news, because coal is very polluting in terms of greenhouse gas emissions intensity, like we have discussed before with examples of Poland. So another important things to notice, the difference between overall and final use is quite small, because luckily our system losses are lower than the average. So this is the only good news. All the others are, we are not performing better than the average. And of course, these are numbers for Italy, and a specific picture for primary energy supply source by source in the last 30 years. And you see that, okay, we are improving, but you must remember that the target for Kyoto was reduction with respect to 1990 of 20%. So we were engaged in reducing the emissions with reference to 1990 by 20%. And we are not doing that. We are just, seeing the effect of the economic crisis of 2008, and basically we are just about the same as 1990. And looking at the different part, we see here some impact, especially on biofuel, that are increasing, and reduction in oil. So what is the perception here is clearly oil is decreasing, which is very good, and also because of constraints, because we don't have internal production, so we are reducing importing of oil from abroad. And at the same time, gas is increasing, and we still do not have gas, so we are importing large share of it, and we are slightly increasing mainly biofuel, that is this line, and slightly increasing solar. So this part is solar, so you can see that is increasing, but not so much. So this is Italy, and of course, once again, I'm showing you the pie in the time, and what you see is that here some differences can be seen, and the differences are in terms of wind, solar, and biofuel and waste again. So basically what you can see here at a glance is that in the last 30 years, wind, solar, biofuel, and waste are covering about 20% of the total, and they are doing that, reducing oil, which is good. But still, you can see that from 2012 to now, things are constant. So there was a huge increase from 2000 to 2010 in terms of renewable. You clearly see an increase, and then it's constant. So after 2010, 2012, production increase of renewables is constant, while in order to fulfill Paris Agreement requirements, we should increase them, making the large majority of the overall energy demand. So Italy is performing better than the average, but still very lagging from the desired results. And in terms of finally energy use, please notice that numbers are the same as average. So every part in the world is the same. 1/3 for transport, 1/3 for industry. You see that we are performing bad in industry, so our industry is not as strong as in the other part in the world. And the largest third, so 1/3, but largest, is on buildings. So these are constant numbers, and once again, gives us the cues to tackle the problem. So if we want to reduce energy, we know that these three buildings, industry, and transport are the area to act on. So once again, we are looking at time trends in terms of consumption by sectors, and you see here things are pretty constant. So basically, there is an important improvement in industry. So industry is reducing its share from more than 30% to about 20% of the overall total. So it's a very important performance by industry. So investment in improvement of efficiency in the industry and reduction of waste, energy waste, is huge. But at the same time, we have an increase in buildings. So our houses are consuming more energy than in 1990. And this is totally incredible. We have a perception that we are doing the opposite. It's not true. In our houses, energy consumption has increased a lot. Also because we have had a large number of new houses, so because of consumption of soil, but also because still we don't have very performing houses. So our houses are still consuming a large amount of energy per unit, so per square meter. And the other picture are quite constant. So this is what is number saying to us. So this is reality. And the reality is we are very far from what would be needed to reduce the greenhouse gas emissions from the energy side, that is more than 3/4. So another important picture, here are number per capita, because absolute number can be confusing, because we can see China increasing a lot, absolute number, but what is important is per capita. So when you go to per capita, you see the real thing. So per capita means what each of us is requiring for his life. So of course, this doesn't mean that each of us use 2.5 ton of equivalent oil, but it is the sum of the energy required for transportation, government, public administration, and industry average per person. So you see here that Italy is overall over the average. And you see once again the phenomena we have discussed so far. So this is the industrial crisis in 2008, but still we are increasing. So at world level, we are still at higher level per capita. And going back to Italy, yes, there is the impact of 2008 that was very huge in Italy, as you all know, but we are restarting. So, okay, COVID is not here, and COVID would be another whole, but yes, we are still roughly at the same level of 1990. So once again, not very good news. At overall level, things are worsening, but even at national level, things are not so good as they should be. And of course, most important is greenhouse gas emission. And here we see that at national level, things are improving. Remember that the target of Kyoto was to reduce about 20%, and we are roughly achieving that target with different periods. So it's not clear if this reduction is caused by economical crisis, but probably yes, and not by virtuous action. But still, at world level, situation is dramatic, it's terrible, because we are about 50% more. So we had 20,000 million of tons of carbon dioxide, and we have now more than 32 thousand million of tons of carbon dioxide. So overall emissions have increased a lot. And remember what I said before, minus 8% because of COVID in 2020. So in 2020, if you look at this picture, you have minus 8%, but already we are now at a level higher than December 2019. So this hole was already recovered by the activities that have restarted, luckily, after the pandemic lockdown. So just to say you that things are not good, neither in terms of greenhouse gas emission, that is the most important things, as other colleagues have shown you in previous lectures, because of the direct impact of greenhouse gas emissions on the climate problem. So probably one of the last picture I'm showing you this Monday, then inviting you to continue next Monday, is about the per capita. So as I said before, the situation is very diverse. So we have really different situations. So you can see here that United States have about 7 tons of equivalent oil per capita. Remember, Italy is about 2.5, and the average is 2, less than 2, 1.8, and so. So you see that in Africa, there are many countries that are almost white, meaning, so the color is proportional to the number of ton of equivalent oil per capita. So you see that the situation is very diverse. You have area like Saudi Arabia, where of course consumption per capita is very high, like in Iceland. In Iceland, numbers are even higher than in United States, but this is clear. The total number of inhabitants is very low, so of course the average is high. But you see very, very diverse situation, and this is of course one problem, because this is the real motivation for migrations. So as an engineer, as a physician, it's pretty clear that every time you see 2 conditions uneven, you have a flow that makes an equilibrium. And here is exactly the situation. As soon as people understand in Africa or in Saudi America, in South America, that there are differences, they move, because this is the flow, the natural flow that follows in every uneven situation, like temperature or others, or pressure. And this is very clear. So it's very clear that migration are a direct consequence of that. So are a direct consequence of the unequal, uneven behavior of economical systems in different countries. And the first index of economical and general situation is energy, as I've said from the beginning of this lecture. So this picture is very important to me to understand this uneven situation. And this concludes section 2, and I have just 3 minutes for your questions or comments. And of course, I will stop here, waiting for questions or comments, and inviting you for the next lecture on Monday 29 at the same hour. I don't see any further comment or questions or any other issues. So
I take this opportunity, Alberto, to thank you once again. And I just would like to ask you a question related to the slides. For the next lecture, next Monday, are you planning to prepare additional slides, or will you use again these ones?
No, I will go on with a slide on section 3, 4, and 5.
Okay, perfect. Sorry, because
We
I didn't.
are now 33 of 85.
Ah,
so
okay, very
probably
good.
my
Because,
pace must be higher next Monday,
okay.
but
Okay, very.
I will do my best.
Okay, very good. And there is also a message on the chat now. Very good. And sorry, because I didn't realize if you got to the end of the slides or not, because I missed part of your lecture. Thank you once again, and I give the word to the student. There is a question.
Yeah, the question is the consumption of N gas after 2010 is not because the increase of N gas production and also the reduction of its price. It means that if renewable energy has more competitive price, it was in better situation now. I'm not sure I grasp the meaning. So the question of Essam is about natural gas. So if I don't understand bad, he is asking about the motivation for increase and is wondering whether the increase is related. So he's commenting on this increase in Italy and is wondering if the increase is related to price. Well, it's hard to say that. Probably there are many geopolitical reasons. So of course we are importing energy and price is a very important part, but also oil has decreased, as you know, in the last time from $100 per ton to even zero sometimes, or negative values. But anyway, the point is, yes, if renewables would have competitive economical values, probably their demand would increase. But this is not the only driving part. So yes, if the price would be competitive, renewables would have a higher penetration, but still price is not the only driver because there are technological problems. So there are, as an example, you are using natural gas in your house for heating, and renewables cannot be directly used in houses because renewables produce electrical energy. So you would need a change of your heating system using electricity. And this requires large investment in houses. And as we have seen, houses are covering and buildings in general 40% of the total of the pie. So price is a driver, but it's not the only driver. So I hope I grasped an answer to your question. So hydrogen. How many hours I have to answer this question, Alberto? If we are starting talking about hydrogen, we would require probably more than half an hour. So I would do two things. One thing is placing a link in the chat to a very interesting lecture given to a colleague of ours, Nicola Armaroli, on the topic of hydrogen. Very recently, I would say 2 or 3 days ago. Sorry, it's in Italian, so for Italian-speaking people would be very clear, and he provides a clear taxonomy of different hydrogen technology and of application. So I would invite you to read that and to listen to that, sorry. And of course, next Monday, I will be happy to provide specific questions. As a general answer, there are colors. So there is green hydrogen, blue hydrogen, brown hydrogen, or even pink hydrogen. What does color mean? So green hydrogen is hydrogen produced by hydrolysis of water by renewables. So you have water, by hydrolysis, you can split H2 hydrogen by oxygen, and this is green hydrogen. Then you have blue hydrogen, which is made by methane. So you have CH4, which is the chemical formula of methane, and you can extract hydrogen from there with a process that is the blue hydrogen process. So this means, and the same is for brown hydrogen, producing hydrogen from fossil fuel. So once again, it's not renewable because you are using other things to produce hydrogen. And the pink hydrogen is the idea of using nuclear energy to produce hydrogen. The general bottom line is that to produce energy, you require huge amount of energy. So typically, the energy balance is negative. You have 100 units of energy at the end, but you require much more to produce it. So the energy balance is negative. And in any case, so green, pink, black, or green. And then we go to the usage. How can be hydrogen used? Typically, hydrogen is a storage. So the typical use is to use it to store the energy, because we will see one of the main problems of renewables next Monday is that it is very intermittent. So there is a huge difference between production and use, meaning that you produce energy during the day and you need it now when the sunlight is over. So you need storage, and hydrogen can be a very efficient way of storage of energy. And this is the main usage. Another idea is to use hydrogen to produce electricity. So there is a technology called fuel cell that is basically a battery made of hydrogen. So you use hydrogen with a specific chemical process that is fuel cell, and you can use this as a battery in your car. So you have an electrical vehicle where the battery is not chemical battery, so standard chemical battery with lithium or others, but it is made by hydrogen. So it uses hydrogen to produce fuel cells. But still, the problem is at the source. So to produce hydrogen, you need a very complex process. Green, brown, pink, blue, but it's very complex and still controversial how we will use it. And there is many discussion on that to decide the better destination. And if you can listen to the Italian description of our colleague, it will be very, very effective. In half an hour, you will have a clear answers on many questions on hydrogen. I'm just looking to the link, and I will provide you the link by Armaroli. So just a moment. Here it is. So I don't know if you have other questions. Here is the link. I don't see other comments or questions, so I will thank you, all of you, for your attention and very, very good questions you placed all along the lessons. So I'm happy to talk to you again next Monday, and hopefully I would need a higher pace, but I will do that.
Thank you once again, Alberto, and thank you to Giacomo and Francesco for the simultaneous translation. I'm waiting, Francesco and Giacomo, for the recording of the lecture. Thank you once again, and see you next Monday. Bye-bye.
Goodbye. Bye-bye.